Hello, I'd like to start by thanking the organisers for the opportunity to speak to you today. My name is Karl Friston. I'm a Professor of Neuroscience at University College London in the United Kingdom, and the title of my talk is Certainties and Surprises in Our Daily Lives, the Brain as a Prediction Machine. And I'm going to deal with certainties and surprises in their most simple form, namely how we resolve uncertainty about our lived world through actively sampling it with our eye movements. It may seem a very simple problem, but in fact, it's a very difficult problem in terms of deciding where to gather information, where to gather evidence for your models of the lived world, your generative models. And that's going to be the focus of my talk. This talk comprises three sections. First of all, we're going to consider the basic imperatives for self-organization in things like us. I'm going to tell this story from the point of view of a physicist in terms of Markov Blankets and a special kind of mechanics that ensues from simply having a Markov blanket. I'm then going to tell exactly the same story as if I was talking to neurobiologists or psychologists in terms of predictive coding on neural networks. And then finally, we're going to turn to the active bit, the active resolution of uncertainty or expected surprise that I hope to demonstrate with a couple of simple simulations, ending with a simulation of eye movements and visual foraging of the visual scene. So let's start with the question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, clearly, we can't answer that, but we can think about the notion of a spatial boundary. And that boundary is incredibly important when we want to talk about the self-organization of anything, in the sense that we have to individuate or separate the thing from everything else. I'm going to read a Markov blanket, the spatial boundary as a Markov blanket to illustrate the notion of a Markov blanket. I've described here a little universe in which these blue circles correspond to some abstract states of a universe, and each state can influence another state, as indicated by these arrows. So what is a Markov blanket? Well, let me identify a set of states, say my states, states internal to me. The Markov blanket comprises the parents of the internal states, the children, and the parents of the children. And this set of states provides an insulation, a blanket that protects or shields you from the rest of the universe in a very particular sense. And that sense is that if I needed to know how my internal states would change, given everything else in the universe, I would only need to know my blanket states. In other words, all the information in the rest of the universe about me or my internal states is on these blanket states. Technically, the internal states are conditionally independent of the external states given these blanket states. I'm going to make another move here. I'm going to split the blanket states into sensory states that influence but are not influenced by internal states, and active states that influence but are not influenced by external states. And with this particular partition, I can describe any particle or any person in terms of their internal states and their blanket states that, I repeat, comprise their sensory and active states. And I can apply that partition to my brain. So my internal states would correspond to all the neuronal activity and synaptic connectivity in my brain at this point in time, and it would influence my actuators, my muscles, my autonomic reflexes, that would then influence extrapersonal or embodied states that then change the sensory states by impinging or impressing themselves on the sensory sector of my Markov blanket, and then those sensations change my internal states. So what we have here is a description of an elemental action perception cycle in which the inside influences the outside vicariously through the active states, while the outside, the external world, influences the inside vicariously through the sensory states. What I want you to do now, though, is forget about the Markov blanket. What we're going to do is do some basic physics and then put the Markov blanket back into play and see what emerges. And what will emerge is something that could be described as a Bayesian mechanics, which inherits from exactly the same principles as quantum mechanics, statistical mechanics, and indeed classical mechanics. So where does all this physics start? It starts with a description of the universe in terms of some abstract states that change, that's what the dot means, as a function of the current state, plus some random fluctuations. And I've illustrated that here by tracing out the trajectory in a state space of 2 dimensions in terms of these thin blue lines here. And this could be at any scale. It could be, for example, electrochemical oscillations in a cell in the brain. It could be the phases of my cardiac cycle, my heartbeat. It could be me getting up in the morning, having a cup of coffee, doing my emails. It doesn't really matter what scale we're considering. The important aspect of this kind of physics is that the state of the system always returns to the neighborhood of a state it was once in. In other words, there is a set of states to which the system seems to be attracted. Technically, this is an attracting set or manifold or pullback attractor. These are the kinds of systems we want to describe. There are a number of ways of describing them. One interesting one is to interpret the density of these trajectories or paths in terms of the probability that you will find me in this state at any point in time. And I've denoted that by a probability density over the states given me. I've done that because physics knows a lot about the dynamics and the behavior of this probability distribution. I've expressed this here in terms of something called the Fokker-Planck equation. We don't need to know what this entails. All we need to know is that because we know about the density dynamics and we are interested in describing things that persist over time, then that means that the probability density itself does not change. So this change of the probability is 0, which means that we can solve this equation in a really interesting way. I've expressed this solution down here basically as a flow, a dynamics, how my states or the universe's states will change as a function that depends upon the amplitude of the random fluctuations gamma, another term q, and a gradient. And this gradient is simply the gradient of the probability density. So it's as if all my states are flowing up probability concentration gradients as if they're countering the dispersive effects of the random fluctuations. So that's the basic physics. What about the Markov blanket? Well, that fundamental gradient ascent or gradient flow up probability gradients has to apply to the Markov blanket partition. And in particular, it has to apply to my internal states and my active states. So I can write down that equation for the internal states and the active states, noting that I don't have to worry about external states because the external states can never influence the internal and active states. And I can read this in one sense as a description of some elemental perception and action that are both trying to, or will look as if they're both trying to maximize the same thing, namely the log of the probability of some sensory states given me. So how could we interpret this quantity? Well, I've just said that the sensory states that constitute my attracting set are exactly those states that you will find me in. They are the states that characterize me as the kind of thing I am. They are valuable to me because I occupy these kinds of states. I'm a particular temperature, I'm not very cold, I have a particular physiology. On that view, we can read this log probability that is being optimized by perception and action as simply as value to me. From that, we can read off reinforcement learning, optimal control theory in engineering, and if I was an economist, it would just be expected utility theory. If, on the other hand, I was an information theorist, the negative of this value is known as self-information or surprisal, or more simply surprise. It just scores the prediction error, the surprise, the implausibility of me being exposed or encountering some sensory events given who I am. This information theoretic interpretation leads to things like the Infermax principle, or principle of maximum mutual information, equivalently minimum redundancy, and the free energy principle. Why the free energy principle? Well, the free energy, variational free energy, strictly speaking, is a bound or an approximation to the surprise, to the prediction error, if you like. And we're going to go into the functional form of free energy at the end of the talk, just to unpack it in terms of understanding how we resolve expected surprise, namely uncertainty. If you're a physicist looking at self-organization and non-equilibria, this is a nice interpretation because the average surprise, the average self-information, is just entropy. So we now can say that perception and action is trying to resist the entropic dissipation or dispersion of states in the spirit of the second law. And of course, this is the holy grail of things like self-organization and synergetics of the kind described by Hermann Haken. And if I was a physiologist, it would just be a statement of homeostasis. It's just keeping my essential variables within some characteristic bounds. There's a final interpretation here which I want to leverage, namely the interpretation that a statistician would bring to the table. And she would say, oh, well, this is just the model evidence. It's just the marginal likelihood or the model evidence of these sensory data given me as a model of how my data were caused by the world, sometimes referred to as a world model or a generative model. And from this interpretation, one can then appeal to the Bayesian brain hypothesis as implemented through evidence accumulation, in particular, things like predictive coding and processing. So that's the interpretation I'm going to pursue, this statistical interpretation, which can be interpreted in terms of a Bayesian mechanics that complements the other kinds of mechanics we find in physics, or you can interpret it in terms of maximizing model evidence through acting and perceiving the world, namely gathering evidence for your world models. So now I'm going to tell the same story, but using constructs and words that will be more familiar to psychologists and neurobiologists, and specifically focusing in on how the brain might conform to this basic principle of self-evidencing, this kind of Bayesian self-organization. This story could start anywhere. I've chosen to start in the 16th century with this oil painter famed for painting still lives that, when viewed from a different perspective, give you a very different visual impression. So if previously you saw a bowl of fruit and now you see a face, what he's trying to say is that you made that face. This is something that you have brought to the table to explain this particular pattern of sensory inputs. What it's telling you is that the brain is a constructive organ. It's an organ that generates explanations, hypotheses, fantasies about the causes of its sensations, that then it can use sensory input to test and revise those hypotheses, explanations, fantasies. It's literally a fantastic organ, a prediction machine, a statistical engine. This notion is probably most beautifully articulated by Hermann Helmholtz as follows: objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. So again, what he's saying is it has to be on the inside to explain your sensory impressions before you perceive it. And clearly this is very closely related to the notions of people like Richard Gregory in terms of perception as hypothesis testing, that perception is active sensing, active vision, where you're using sampling data and using the sensory data that you have sampled in order to verify or revise your beliefs, your hypotheses, your explanations for your sensed world. And these ideas have been used to great effect in machine learning by people like Geoffrey Hinton and Peter Dayan, and indeed they built a Helmholtz machine as an analog, a mathematical image of the Bayesian brain borrowing from Bayesian probability theory, and in particular using Richard Feynman's free energy as a way of being able to calculate the requisite surprise or self-information, the negative value. Let's come back to Helm, Holtz, and the notion of impressions on the nervous mechanism. From our point of view, from the point of view of the Markoff Blanket partition, this means that if this Bayesian mechanics is right, if this interpretation of self-organization as self-evidencing is the right way to read our internal and active dynamics, then it means if I was exposed to this sensory impression, this shadow on my sensory veil or the sensory sector of my Markov blanket, it would look as if I was compelled to find a good explanation for this, to make sense of it, to explain it on the inside. So how could the brain do that? Well, we know the dynamics and we know the mechanics because the brain is just a set of internal states. So I've just written down our fundamental gradient flow equation here. Here I'm substituting the free energy for the self-information or surprise. And again, we'll come back to the functional form for the free energy later on. At this point in time, we just need to know that the rate of change in my internal states, in my neuronal dynamics, can be described as if it was trying to do a gradient descent or minimize my free energy. I've written it down there, and I've written it again in a form that if you were an engineer, you would understand as a Bayesian filter, specifically a Kalman filter that has two parts to it. This is the part called a prediction part that effectively says that if I know or have some beliefs or expectations about the state of the world, I also have some prediction about how that world will change. But I can update that prediction on the basis of what I'm actually sensing in the moment. And I've replaced the gradients of the free energy with prediction error here. So what is prediction error? Well, imagine we had this sensory impression on our retina, on our eyes. Imagine further that my brain state encodes an expectation or a belief that this sensory impression was caused by a howling dog. And if my internal dynamics were such that they could be read as a generated model that generated predictions of what I would see if I was right, then I can simply subtract my predictions, the predictions of the generated model, from what I'm actually sensing, and the difference is the prediction error. It's simply the mismatch between what I'm sensing in the moment and what I predict I would sense if my beliefs were correct. And all this equation is saying is that the prediction error will now look as if it's driving changes in the neuronal dynamics and implicit representations in order to resolve or eliminate, at least minimize, the prediction error. And if I can do that, I've now got a good enough explanation of what caused my sensory impressions. Now, clearly, I will never know the external states because they are hidden behind the Markov blanket. But as long as I can keep my prediction errors low for as long as I survive in my world, job done. That notion of prediction error, free energy as prediction error, I think is really useful. It means we can forget about all the physics and just understand action perception in the service of minimizing prediction error. And there are two ways we can do that. We can either literally change our mind, change our neuronal activity to generate predictions that are more like the sensations, or we can actively resample the world to make our sensations more like the predictions. So this offers a view of action as changing sensations that fulfill predictions, where the predictions are formed based upon perception, namely changing our expectations about the causes of our sensory input so that they minimize prediction error. Just to put a bit of flesh on that in terms of how we think these processes unfold in, say, the human brain, I've cartooned a visual system here that has a certain hierarchical structure, but conforms exactly to this fundamental dynamics that we're now reading as predictive coding or a Bayesian filtering procedure in terms of passing messages between prediction error populations and those populations that encode the expectations that generate the predictions. So let's just consider visual input from the retina. It comes in, enters at the level of some subcortical bodies or nuclei, in this instance the lateral geniculate, and is in receipt of top-down predictions from the primary visual cortex. And then this population of nerve cells compares these two, produces a prediction error that then is used to revise representations or expectations in the visual cortex. But these representations or expectations are themselves being predicted by higher order expectations, generating a second order prediction error that then, in exactly the same way, drives or revises the expectations at the higher level, and then so on to any hierarchical depth required in any deep or hierarchical model associated with, in this instance, human neuroanatomy. That's good for perception. What about action? Well, let's consider another kind of input, proprioceptive input. And by proprioceptive, I mean the kind of input that reports the states of my effectors, my actuators, my muscles, my autonomic nervous system. And in this example, coming from, say, eye muscles. And this arrives at the pontine nuclei and may be in receipt of top-down predictions to form a prediction error in the usual way. And this prediction error could be used to revise my beliefs about where my eye is pointing. However, there's a much simpler way to resolve this prediction error. I can just use it to directly drive the muscles that are generating the proprioceptive signals. In other words, I can contract or relax my muscles until they are generating or recording exactly the signals that I predicted. So on this view, the top-down predictions basically supply a control signal or a set point for classical reflex arcs that fulfill the predictions, effectively using a closed-loop reflexive kind of action to minimize a very small part of all prediction errors, namely the proprioceptive prediction errors, but in a way that is deeply informed by assimilating, accumulating evidence and making the best sense of this in a deep world model or generative model entailed by the brain. So that's the basic setup. I just want to close by illustrating the kind of behavior that you can get or simulate under this merely reflexive kind of active inference or active sensing, self-evidencing. This is one of my favorite examples because it illustrates a number of biomimetic and biologically plausible features, but it also illustrates that we often author our own sensorium. We are actually generating much of the interesting sensations that we're making sense of. So in this example, what we have done is equip an agent with a central pattern generator with some autonomous dynamics. And these dynamics, according to the agent, will move an invisible point in extrapersonal space. And the agent believes that her finger is attached to this invisible point by an invisible spring. So she expects to both feel and see her finger being pulled around in an itinerant fashion. And when looked at from the outside, this looks very much like structured handwriting, as illustrated down here. So this nicely illustrates the role of descending predictions from some autonomous generative model, proprioceptive predictions that are fulfilled reflexively through classical motor reflex arcs that change the external states, that then provide the visual inputs that themselves are being predicted by what some people refer to as corollary discharge. This is a nice simulation because we can intervene on the simulation and remove the proprioceptive prediction errors. So what would that be like from the point of view of the agent? Well, from the point of view of the agent, she can still see something being written, but cannot feel herself moving. So it would be as if somebody else is doing some writing, but of course, she has exactly the right kind of generative model and dynamics that enables her to predict very accurately what will come next and what is happening in the visual domain. And this is often interpreted in terms of action observation, observing the same kind of action that you yourself would prosecute, but using exactly the same neuronal machinery to explain both the observed action and the prosecuted action. And there's a wonderful literature called the mirror neuron literature detailing this physiologically. There are all sorts of other interesting features, such as place selectivity, directional selectivity, that emerge simply from simulating or solving these predictive coding equations that themselves inherit from the Bayesian mechanics. I want to close, though, by noting that this kind of reflexive action, although very expressive and interesting in terms of understanding neuronal dynamics from a computational perspective, doesn't really speak to the way that we resolve uncertainty, the way that we would plan in order to seek information in a way that maximizes our understanding of the world and what is causing our sensations. So how would we get to that kind of resolution of uncertainty from the point of view of the physics, or the sentience that I've described in terms of the Markov blanket? It's actually quite simple to do. All we have to do is to consider sufficiently large, complex creatures like ourselves, where the internal states now become divorced from the Markov blanket, and in particular, the active states. So if I just remove this arrow here, now we have a very different situation in which the active states look as if they become causes of my sensations. And if I can read my internal dynamics as basically predicting the causes of my sensations, that means I can read my internal neuronal dynamics in terms of actually inferring or predicting my own action. And this draws a bright line between certain simple forms, very small forms of biotic self-organization that have this reflexive like aspect that we illustrated with the mirror neuron simulations of the previous few slides, and we move to a much more interesting kind of architecture and self-organization, in which effectively we can think now of a creature holding beliefs about its own action. And this leads to the notion of planning as inference, in which updating beliefs about what I'm going to do now becomes part of sense making. And it becomes part of sense making in a particular way, because I have beliefs about subpersonal beliefs about my behavior, I have to have prior beliefs. So a priori, what do I think I'm going to do? Well, I'm going to minimize surprise. More specifically, I'm going to minimize the surprise I expect following an action. Mathematically, we can write this down in terms of an expected free energy that bounds the surprise, and we denote that usually by G. So at this point, I'm going to, I'm afraid, present some horrible equations, but to my eye, these are beautiful equations. The equations have been presented iconically just to illustrate the beautiful symmetry between the imperatives for sense-making perception in the moment, as scored or defined by the variational free energy, and the imperatives for acting as defined by the expected free energy of a particular action A. So what do these equations mean? Again, ignore the maths, just focus on the interpretations of the terms, which is the interesting thing here. If I was a statistician, this surprise, this prediction error, this variational free energy is basically a score of the goodness of my predictions of data. Now, those predictions have to be accurate, but also they have to be minimally complex in the sense that I have to minimize the departure from my prior beliefs when changing my mind to give posterior beliefs that provide an accurate account. So in this sense, we can actually write down the free energy as effectively complexity minus accuracy. By just rearranging two of these terms, I can write it in a way that people in machine learning would immediately recognize, namely as an evidence bound. So this log probability of states, hidden states of the world, or the sensory states on the sensory sector of my Markov blanket, if you remember, is the log evidence. And this is another divergence term measuring a difference between one probability density and another probability density that can never be less than 0, which is why it's called a bound. There's always an upper or a lower bound on the log evidence, known as an elbow in machine learning. The reason I'm going into that is if I now take these quantities, the complexity, the accuracy, the divergence, the log evidence, and ask, what would these look like if I took the expected values under some predictions of the outcomes I might get if I did this? And I've written this down to show that the complexity in expectation becomes risk, the inaccuracy becomes ambiguity, and the divergence and log evidence become intrinsic and extrinsic value, respectively. So what on earth are these terms? Well, in fact, I'm sure most of you will actually recognize them if I just explain them. Let's make our life easier and ignore the log evidence or the expected extrinsic value here, and just focus on this term here. This is another, what's known technically as a KL divergence, a relative entropy. From our point of view, it just scores the difference between two distributions, namely this one and this one, and has a very particular and intuitive explanation. It's effectively telling you about the information gain afforded this action in terms of the difference between my beliefs about the external states, given the sensory states that would ensue if I did this act, relative to my beliefs in the absence of the sensory consequences of this act. So technically, it's an expected information gain. It's the degree to which I resolve uncertainty about the causes of my sensations, also referred to as intrinsic motivation in neurobiology. In ethology, you could read this as epistemic affordances, the degree to which I can resolve uncertainty or expected surprise by doing this as opposed to that. In the visual search literature, it's known as Bayesian surprise. In information theory, it's just the mutual information between the causes, external states, and the sensory consequences on my Markoff blanket. So that's nice. Let me make things a little simpler for ourselves and remove another kind of uncertainty from the table by removing ambiguity. What does that mean? Well, it just means I'm going to assume that I can see all the external states, the sensory states and the external states that are hidden behind the Markov blanket are no longer hidden. I can see everything. So S becomes eta, and now we're left with risk. What is risk? Well, it's another divergence. It's just the difference between what I predict or anticipate will happen if I do this relative to my preferred states that are characteristic of me, my prior preferences, if you like. This is known as KL control in engineering. In economics, you could read this as risk-sensitive control. The kind of planning, the kind of control, the kind of policies you get in the absence of any ambiguity. Finally, let's remove all uncertainty from the table. In other words, I'm now going to ignore even the intrinsic value. So I'm going to assume there's no more reducible uncertainty. I'm just left with this term, which we know from the first principles account at the beginning. It's just the expected value. If you're an economist, this would be a statement of expected utility theory. So let me close just by illustrating the way in which we can simulate how brains deal with surprise and uncertainty by using eye movements, by choosing where to look next, to palpate the world in a way that responds to these epistemic affordances, to this intrinsic value, to this expected information gain. And we can calculate exactly what this is as a function of where we're looking. Say we can only sample a small part of the visual field and ask how much information gain or uncertainty do we resolve given this information about the cause of my sensation. For example, it could be this face here. And I can move this around and evaluate the intrinsic value, the expected information gain, or the epistemic part of the expected free energy for every location, and produce what could be read as a salience map. And indeed, this salience map looks very much like the map that would attract human eye movements in empirical experiments here, classic experiments of Yarbus. So can we simulate this kind of behavior just by integrating those predictive coding equations, but now equipping the generative model with the consequences of action, namely, what would I see if I looked over there? And we can do that quite simply. This is an example in which the simulated agent has a very simple universe. She could be looking at an upright face, a sideways face, or an inverted face. Crucially, she can only sample local parts of the visual scene at any one time, and has to choose very carefully, in accord with this salience map, with this epistemic affordance, where to look next to resolve the most uncertainty about whether the state of the world, hidden state of the world from her point of view, is this, this, or this. And this is where she chooses to look at the most informative parts of the image, and these are the sensory samples solicited actively from this visual palpation. And as time goes on, she accumulates evidence resolving her uncertainty about what is the underlying cause of this sequence of saltatory epistemic samplings of the world. And that's the basic story. That's my account of uncertainty and surprise in our daily lives. An elemental example, I know, but it's something we're doing 4 times a second. So the brain is a remarkable machine, a truly fantastic organ. In summary, we are all self-evidencing creatures, namely seeking evidence for our world models, and we act in a way to resolve uncertainty, namely maximize information gain. I'll give the last word to Helm Holtz, who states this much more eloquently. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it just remains for me to thank you for your attention. Thank you very much. Thank you and goodbye.